we introduced the paper, Adaptive Human Matting for Dynamic Videos. The model is named AdaM, Adaptive Matting. Video human matting aims to estimate a precise alpha mat to extract the human foreground from each frame of an input video. In comparison with image matting, video matting presents additional challenges, such as preserving spatial and temporal coherence. In order to solve the video matting problem, a number of approaches have been proposed, including image-based, trimap-based, and manual-free methods. However, there are limitations in these frameworks. A straightforward approach is to build on topic image matting models, which is to implement an image matting approach frame by frame. In this way, alpha mat predictions can become inconsistent over time, resulting in flickering. Alternatively, top-performing methods leverage dense or sparse trimaps, which is expensive and difficult to generalize across large video datasets. The process of creating trimaps limits these methods to real-time applications, such as video conferencing. Recently, more general solutions, like MODNet and RVM, have been proposed which involve manual free matting without auxiliary inputs. In some challenging real-world videos, it's hard to differentiate foreground and background at some points, causing these solutions to produce blurry alpha mats. The objective of our method is to produce accurate alpha mats in challenging real-world environments without requiring manual input. To do this, we study the framework for explicitly modeling the foreground and background. Our framework includes an off-the-shelf segmenter, an encoder-decoder network, and a foreground-background structuring transformer network. Given an RGB frame, the encoder extracts low and high resolution features. At the first frame t equals 0, the segmenter obtains an initial cause mask for embedding into the initial key and value feature map. The transformer network employs long and short-term attention to explicitly model foreground-background appearance. Then, the decoder concatenates the foreground-background features from the transformer and the high-resolution fine features from the encoder to produce an intermediate mask and a final foreground alpha mat. Lastly, the newly predicted foreground-background mask is used as a new reference mask to update value adaptively. The contributions of our papers includes: we propose a framework for human matting with unified handling of complex unconstrained videos without requiring manual efforts, like manually annotated trimaps or pre-capture backgrounds. Also, the proposed method provides a data-driven estimation of the foreground masks to guide the network to distinguish foregrounds and backgrounds adaptively. Moreover, our network architecture and training scheme have been carefully designed to take advantage of both long and short-range spatial and motion cues. Finally, our method reaches top-tier performance on the VM and CRGNN benchmarks. Qualitative comparisons are shown in the following figures. The proposed method is compared to two other methods that do not require manual inputs, MODNet and RVM. The top figure compares alpha mat predictions. It shows that our method is able to produce alpha mats with fine-grained details. The bottom figure shows that our model produces less undesirable artifacts and more consistent alpha mat predictions. The experimental results on VM dataset are summarized in the table. It shows that, without training on high-definition data, our method outperforms previous state-of-the-art methods in most metrics, by a considerable margin in both VM sets. To evaluate its robustness and generalization to real video datasets, we compare the mating quality of MODNet, RVM, and our method to the real dataset, CRGNN. Based on the table, our method is competitive with these leading methods, demonstrating that our method can overcome the domain shift problem and generalize better to real-world data. Here is the video demo with real-world data.